Okay, so on we continue in our life in the endless section, the never-ending story of 6.3. So today what we get into is a different kind of logarithms. So we came in a couple days ago, we had e's going to a power. We had a thing called natural logarithms, which is ln, which has a button on your calculator. But there's other kinds of logarithms, and in trig we usually start with these other logarithms and then get into the ln. Calculus does the reverse, but it doesn't really matter. Okay, but if we have other numbers other than e going to powers, there's other types of logarithms with other sorts of bases, and those are inverses of each other. How this came about was to try to solve things like this. So if we wanted to figure out what this x is, you'd probably use your fingers and go 2 times 2 times 2 times 2 is what I'm doing to get 16. What power of 2 will do that for me? 4. Because 2 times 2 is 4, times 2 is 8, times 2 is 16. If I gave you this one, this would be 5. We didn't need logarithms to be invented, we just needed fingers to be invented to do those. But if I would say 2 to the x equals 20, that's not going to work out for us. Okay? We know that that would have to be bigger than 4 and smaller than 5 because it lies in the middle there, but this would be like 4 point something that without some new math being invented, people just couldn't figure that out, and logarithms got invented. This doesn't necessarily matter to your day today, I'm just trying to remind you of some stuff. So we spent some time in trig. I'd give you something like this, and you'd give me back something like log base 2 of 8 equals 3. Those two, in elementary school, they'll refer sometimes to fact families. Okay, those two are in the same fact family, like 2 plus 4 equals 6. So 6 minus 4 makes 2. Those are both the same fact family. It's forward and backward, inside and out, but they essentially mean the same thing. 2, I give you 4, you get 6. We take the 6, we take back 4 away, we're back to the 2. They're the same. These are the same. 2 to the third makes 8. In the power problem, this is called a base. In the logarithm problem, this is called a base. The 8 got its turn to be alone, the way the 6 did, so now it's more in the mix. 3 gets its turn to be alone, because previously it was in the mix, kind of like how the 4 here is kind of like the 2 here. They stayed there. But the other numbers are kind of like transposing. That's what logarithms are about. Something like this, we used to solve this in trig days by, we would do the log on this side, we would do the log on this side. Powers, we've learned, whether it's ln's or regular logs, can slide to the front, and then those would be multiplying. So you'd have to divide. And you could grab a calculator and do the log of 20 and divide by the log of 2, and it would give you, 4 point something. None of that really affects your life today, but that's just things we've been through, things that are sort of touched on again now. Other numbers to powers, logs with other bases, those are just things. A thing I should probably mention, on the calculator you have a button that has a logarithm, log button. That has an invisible base of 10. If you ever see a logarithm problem where they haven't written a base, the base is 10. You've been dealing with the ln button or the ln writing. That's a logarithm with a base of e. And instead of writing logarithms with bases of e, they've been writing ln's for natural logarithms. I'm supposing the French are probably involved in the naming of this, because the French, as you know from your French class experiences, are sort of notorious for having the adjectives afterwards. So this was probably like logarithm naturale or something at some point, and they just got named opposite of English being a natural logarithm. But here's a couple facts that rule our day. So here comes things that do impact your life. Because these things are opposites, if we have the log of a certain base, and then that base is going to a power, the log with the base will wipe out the base with the power, because they're opposites, the way adding and subtracting are opposites, and you just get the power left. And likewise, if you have a number going to a power, and the power has a logarithm, and the logarithm has the same base that the power has a base, those also just eliminate each other, and you write the power down. It's exactly like what we saw with e's and ln's. We saw a few questions like 2-3 days ago where it was like e to a power and the power had an ln, and we just nullified those. Or we had ln's and then e to a power, and we nullified some things. Example 8 in the book is going to give us some practice at this, so we'll just peek in the book. I'm on 365 if you want to grab the book and join me on 365. They're just going to sort of show you how that works. Pause for a second as people flip. So 365, example 8a, they have a log base 2. And then the 2 is the base for a power problem with a 5. You just eliminate everything but the 5. B has a log base 10. And then a power problem with a base of 10. So just eliminate everything except for the -7. C is written backward, but same concept. It's 2 to a power. The log has a base of 2, so just erase everything but the 3. And then D, same thing. 10 to a power, log base 10, eliminate everything but the 4. Question about those two ideas? For calculator purposes and just other purposes, sometimes it's helpful to have a way out of log base whatever of x. And there's two ways you could use your calculator or just with writing on a paper to change this. Log base a of x is the same as the ln of x divided by the ln of a. So if you needed to punch into your calculator something like this, log base 2 of 8, you could punch in ln 8 divided by ln 2. And that would be a way you could access the 3. You could also use the logarithm button to do the same thing. Our calculus book prefers this in practice for some reason, but the logarithm button would do the same thing. We could do logarithm button with x divided by logarithm button with a. So there's an example 9 to peek at. So example 9, they say basically we want to come up with a number for log base 10 of 2. So if you want to punch buttons along with them, you could. To do log base 10 of 2, you could punch the ln of 2, which is whatever, divided by ln of 10, which is whatever, and when you divide it, you could get 0.3. On a calculator, you do that in one big swoop. The ln button is like the trig button. As soon as you type it, it gives you parentheses. So if you want ln of 2 to divide ln of 10, ln of 2, you'll need to end the parentheses before you divide. Then you hit ln and it gives you that again. You do the 10. Since you're at the end of the line, I don't think that ever matters if you put the parentheses on there, but it never hurts you. Question about that? Then here's two super stars that you want to put on your card. So we've been doing derivatives of ln's. How have we done derivatives of ln's? Correct. Derivatives of all ln's are fractions, original to the bottom, and its derivative on the top. Derivatives of other logs, it's almost the exact same thing. We're going to do the original thing on the bottom of a fraction again. We're going to do the derivative of that thing on the top again. But on the bottom, we're going to throw in the ln of whatever the base is. So if the base is 2, ln of 2. The base is 3, ln of 3. And those are just numbers. Like the ln of 2, ln of 3, those are just numbers like the square root of 2 or the square root of 3. Obviously, you prefer to see 2. Okay, if you're going to see a number, that's more fun. But eventually in your life, you've adapted to the fact that the root of 2, although that's a sort of weird number when made a decimal, it's still just a number. The ln of 2 is also just a number, just like the sine of 2. It's just a number. They become weird numbers, but they're just numbers. But that's a superstar idea. And then there's an example 10. So example 10 says, do the derivative of the log base 10 of this whole big thing. I wouldn't go through all those steps. Okay? As soon as I saw example 10, that I'm supposed to do the derivative of a logarithm, I'd make a fraction bar. I'd put the original 3x plus 1 on the bottom. I would do its derivative on the top. And since I have a bunch of stuff on the bottom, I need parentheses. And I'm going to do the ln of 10 because the base on the problem was 10. So essentially, it's an exact replay of what you've been doing with your natural log derivatives. The only new tidbit of this is you need an ln of that number on the bottom. Other than that, it's the exact same process. Something about that. Then the last superstar tidbit, also card-worthy, is we did a few days ago derivatives of e's to powers. How did we do a few days ago the derivatives when e's went to powers? Yeah, we just copy the original thing, and then we did the derivative of the power. And we're going to do that today as well. But what's going to be new today is we're going to throw on an ln of that number, whatever that number may be. And there's an example 13 that shows this. So like example 13, there's an a part. So when they want the derivative of 3 to the x, they would copy the 3 to the x. They would think about the derivative of the power, which would be a 1, so they didn't write it. And then they wrote an ln of 3, because 3 was the magic number. B, they did about the same thing. You copy the 3 to the power. You multiply in the derivative of the power, which would be a -1, so they just put in a negative sign. And then they did an ln of 3. For C, they copied the 3 to the sign. They did the derivative of sign, which is cosine. And then they just wrote an ln of 3, because the number was 3. It does not matter what order you put the stuff in. It doesn't make any difference who goes where. But you'll have a bunch of pieces multiplying. The original thing is going to multiply the derivative of the power, is going to multiply an ln of whatever the number was. And that core issue isn't, none of that is like super hard or new or really shake your world much. What is going to shake your homework world is the same thing that shook your homework world on the other days, is they're going to take stuff like this and mix it into a product rule, or a quotient rule, or a chain rule, or like a bigger problem, and then you're going to get a little bit shaken, not so much by this as you are just, product rule makes life twice as hard, and the quotient rule probably makes things 3 times as hard. It is what it is. We usually spend 2 days here doing things. We don't have to, but we can. So first objective would be to work odds from 53 to 75, still on the same page. And we're going to skip 65. Go ahead and flip to 371. Look at 65. And then I'll just say, you're welcome. You're welcome. We're going to take a pass on that one. I'm supposing the way to approach that is probably something to do with logarithmic differentiation or something maybe, but that one looks pretty nasty, so we're just going to take a pass on that. If you do the odds, check them in the back, and you're like, no, I got this, then we can move up to 6-4. That's okay. If you do the odds and you're like, I don't know about some of this, then we could spend a day and do the evens before we move up to 6-4, but maybe I shouldn't say we usually do that. That actually feels maybe more like 50-50 to me. I think sometimes we do that, sometimes we don't. But you can make that call as to whether you're feeling like a little more repetition would be A, helpful, or B, a waste of your time. The syllabus doesn't even list that as a choice, so it's not necessary. That can be your call. Question about the new info at all?
Is the logarithmic whatever we did yesterday, is that still in play for like this stuff today?
It could be in play any day, possibly, but I don't think it's going to get used today. It's going to get used sparingly. Okay. But if you see a chance and you want to do it, it's never out of play. But you aren't going to see a ton of product, quotient, chain rule at the same time, combos. But if you do, that's the way to do it. But yeah, that's not going to be a superstar. It's a nice tool in the toolbox, but it's not going to be a thing you're going to use you're not going to use that nearly as often as you just use the normal product rule or use the normal quotient rule change.
Should I cut the recording or keep going? Or
No, we could cut it here.
Okay.
That little tidbit doesn't hurt any. Anything I can do from the